So I'll introduce our second speaker of today. Her name is Jeong Jane Park. She's a Dickey Presidential and Schmidt Fellow here at Princeton University, where she also happens to be my lab mate at Ali Yazdani's lab in the Department of Physics, where she's doing STM studies. Before that, she did her PhD at MIT, where she studied moire materials. And I suppose she's going to teach us more about that in her talk today, titled Emergent Quantum Phenomena in Moiré Superlattices. So let's welcome Jane to the stage.
Okay, good morning, everyone. It's a great pleasure to be sharing some of the things today, mainly revolving around emergent quantum phenomena in Moiré superlattices, actually particularly on magic angle twisted graphene materials. So I actually like to start any of my talk with like a broader motivation, just for fun. So as physicists, we all want to understand the world, right? And when we try to understand the world, what we often consider are different degree of freedoms, like this. And we have existing theories for pretty much all of these different degree of freedoms now. But does that mean we understand everything that's going on in nature? The answer is obviously no, and that's because if you have even just a few different degree of freedoms, that leads to new and unexpected phenomena, the so-called emergent phenomena. And as we are all very familiar with, in condensed matter physics, this sort of emergence mostly manifests itself in the so-called strongly correlated materials. So even though we have just like one type of elementary particle, like electrons, their strong interactions lead to highly degenerate ground states from which different kinds of emergent phenomena occur. Okay, so strongly correlated materials are of our interest. Then how do we study this kind of strongly correlated physics? So the conventional way is to synthesize these so-called quantum materials. The bulk quantum materials has a lot of different possibilities with all these different combinations of atoms in the periodic table. So many different physics was found, and this is still being found in these quantum materials. And when you make these material, oftentimes you have many, many electrons in this material, which is exactly what we want, because we're all interested in many-body physics, right? But now the question is, then how many is many? Okay, depending on the exact number of the electrons in the system, very different kinds of phenomena can occur. This is already evident in this very famous phase diagram of copper oxides, where you can continuously tune from anti-ferromagnetic insulator to superconductivity just by changing the number of charge carriers in the system. Okay, but experimentally, what this means is that for every single point on this x-axis, you have to make different samples by changing the ratio of these different chemical compositions in your materials. That's called doping with chemicals. On the other side of our field, or slightly related but distant field, there's this thing called cold atom systems, where you can basically create artificial lattice potentials made out of laser beams to try to mimic the actual crystal lattice. And with this kind of thing, you can simulate very similar kinds of strongly correlated physics that's found in quantum materials. So then now the question is, can we achieve this kind of doping tunability that we have in cold atom systems, but in real kind of materials? And as we're also very familiar with, I would say a very good candidate for this kind of purpose is to use two-dimensional materials. And that's because, first of all, the doping process becomes so much easier. Just by putting the metallic gate nearby, you can accumulate charges in the interface and control the number of free charge carriers in situ just by applying the gate voltage. And further tunability comes from the fact that you can stack any number of these two-dimensional materials on top of each other to create this composite heterostructure, whose property can be very different from the constituent layers. And it doesn't just stop here, as you already saw in the previous lectures. We have one more tuning knob, which is a twist angle degree of freedom. You put two hexagonal lattices, and you see this longer range so-called Moiré pattern appearing, from which many different kinds of interesting physics can be discovered. So today, I would like to sort of talk about the capabilities of using these 2D Van der Waals materials in the context of finding and discovering new exciting phases of matter or materials, trying to understand them and learning from them in a way that can actually lead to even more exciting physics and hopefully better materials. And for this purpose, I would actually like to take this magic angle twisted graphene family as an example today to sort of show you how we got to discover this class of materials and what kind of questions were there in the beginning. And after sort of talking about that, I'll move on to sort of trying to answer different kinds of questions. But now, by using the Van der Waals materials, not just as a material system under study, but using them as sort of a measurement platform in itself, okay? So in particular, I'll talk about how we got to answer questions about the underlying electronic structures in this magic angle twisted graphene family using the thermodynamic measurements, and also about the superconductivity using the simultaneous tunneling and transport measurements, but entirely based on the Van der Waals device-based multimodal measurement techniques. Okay, so you already heard like 1,000 times in the last 3 days. So when you twist 2 layers of graphene, you can basically form these sets of flat bands near zero energy. When you reach the twist angle of around 1.1 degrees, that's called the magic angle. And when you have this flat band condition, what it means is that your kinetic energy will be, your thermic velocity of the electrons will be almost quenched, and the electrons are going to be reluctant to move in space, and they're going to be sort of like stuck at these AA spots. Okay, so that's going to lead to strong interactions between them compared to the kinetic energy that they have in the system. And sort of one point that I just want to go over just before looking at the actual experimental data is that when we twist these materials, what happens in the momentum space is that you folded and formed this mini Brillouin zone. And in this mini Brillouin zone, you still have this 2-fold spin degree of freedom and 2-fold Valley degree of freedom. Therefore, the total 4-fold spin and Valley flavor, or some people have isospin degree of freedom, inherited from just monolayer graphene. Okay, so this means that in real space, you would have 4 electrons or 4 holes per Moiré unit cell to fill each of the flat band in either direction. So this kind of 4-fold degeneracy is not just for twisted bilayer graphene, but also applicable to twisted multi-layer graphene, no matter how many layers you have. Okay, so just to orient you once more in this context, here's the conductance plot as a function of charge density. And just once again, this 0 is called the charge neutrality point, which is basically sort of this level that's in between the 2 flat bands. And then either as you go to the right side or the left side, it means you electron dope or hole dope, meaning you just go fill up this upper flat band or the lower flat band. And then there's this sort of nomenclature that we use new called the filling factor, which ranges from 0 to ±4 in this particular diagram. And that 4 is the same 4 that we talked about in the previous slide with the 4-fold degeneracy of the flavors. So this means that, once you reach this ±4, you reach this band edge, okay? So it makes sense that you have this conductance minimum because you literally have this band insulator. So that's called a full filling. But the surprising thing that happened in 2018 was that even when you just half fill this band where there's no band insulator, you still have this suppressed conductivity, which is the correlated insulator, the insulator gap that's formed by the strong interactions between the electrons and the flat bands. And in the same material, as you've already heard, there was also the superconductivity that was discovered near this correlated insulators space. And after that, there's so many different phases discovered within this single flat band. There's like correlated insulator, superconductivity, topological phases, or even magnetic phases as a function of filling factor, temperature, and magnetic field in this system. So the whole point is that you can reach all these different phases just by in situ gating in this single material and single sample. So if we come back to this first slide, we can see that there's this new platform called Moiré quantum matter, which has the length scale and the temperature scale that lie between these 2 existing platforms for studying strongly correlated physics, but with pretty good in situ doping tunability in this real material system. Okay, so and since the discovery of magic angle twisted bilayer graphene, there were so many phases found, and there's also so many more to this, but this is sort of like I'm trying to do like a historical view. So, but for the first few years, since the discovery of magic angle graphene, The robust superconductivity was only still found in magic angle twisted bilayer graphene, even though there were signatures in other types of twisted Moiré systems back then. Even though all these other, many of these other platforms also have very flat bands. Okay, so that was sort of the status in like 2020, 2021. So then that led to a lot of questions of like, then why, what is so special about this magic angle graphene in terms of forming the superconductivity? Like, is it, the particular symmetry of the system? Does the flat band have to be isolated from the other bands? Like, or does the band have to be like really, really flat? Or is there like a particular electronic structure that forms that's very important for formation of the superconductivity? So those were sort of the questions that were lingering in the field at the moment. And we wanted to answer those questions, okay? We wanted to see, what are the actual important ingredients for forming this kind of superconductivity. And when you try to just answer these questions with one system, that's kind of hard. So we decided to make sort of a new Moiré system to be able to discern what's the really important factor, okay? And when you try to do this kind of thing, oftentimes, you want to keep some of the things the same and only vary some other things so that you can at least like compare like, well, what was the important factor? So we decided to keep the symmetry of the system, which was the C to T symmetry that was present in magic angle twisted bilayer graphene. But we decided to change the fact that the flat band was isolated. So now we're going to make a system where the band is coexisting with other flat bands, okay? And then the flatness of the band and electronic structure, we wanted to make a system that we could actually tunably change these properties of the band structure in situ, in addition to the built-in control. So those were sort of the agendas in making a new Moiré system. So there was sort of the first part of the talk where we made this so-called magic family. So the first system that we looked at is this twisted trilayer graphene structure, where you have 3 layers of graphene now, and the adjacent layers are twisted by theta and minus theta, such that the top and bottom layers are aligned, and the middle layer is at a relative twist angle, okay? And this system actually has an extra symmetry, that's a mirror symmetry of the system that was not present in twisted bilayer graphene. Okay, so how do we understand this kind of 3-layer twisted structure? Like in general, if you have multiple layers twisted with respect to each other, it's much harder to calculate a band structure because you might have different Moiré periodicities in the different interfaces, and then might also form super Moiré and so on and on and on. But in the case where we have this symmetrical twist, where it's twisted by theta and minus theta, we would only end up in a single Moiré periodicity. And in this case, we can actually simplify the original Hamiltonian into a block diagonalized form, where you have a block that can be like a magic angle twisted bilayer graphene-like block, and a separate coexisting monolayer graphene-like block. And this means that we can actually decompose this twisted trilayer graphene structure into a combination of twisted bilayer graphene-like structure, but then with this square root of 2 larger interlayer tuning factor, which came from the block diagonalization, plus a monolayer graphene. So this, because of this square root of 2 larger interlayer tuning factor, here the magic angle for making this particular block a flat band-like block would require the angle of the twist to be exactly square root of 2 larger than the magic angle twisted bilayer graphene angle. Okay, so 1.1 times square root of 2 results in 1.56. And when you calculate the band structure for this kind of system, this is sort of what you get. So you have this orange band, which is from this magic angle twisted bilayer graphene-like block, exactly what we expected, just similar to what we already saw with the flat bands and the remote bands. But what's coexisting is this pristine monolayer graphene-like Dirac band that's like sort of happening at the same time. So that's sort of how you can picture this system. And we experimentally realized this system, and we found, the combination of absolute zero resistance shown in this temperature dependence measurement, as well as the sharply switching IV curves. And also when we apply small out-of-plane magnetic field, you see these oscillatory patterns. These are called Fraunhofer patterns. So the combination of these 3, and I would say honestly, like only when you have the combination of all 3, you can claim that your superconductivity is a real 2-dimensional superconductor. Okay, so we found another system that is another Moiré superconductor. So that's already kind of cool. But that's not it, because we wanted to answer more questions than just that. So we wanted to sort of make use of this further tunability of the in situ band structure control. So we already looked at this band structure where you have this pristine, Dirac band that's coexisting with your flat band originally, where when you don't apply any like external fields to the system or perturb it in any other way. So that's the status. And the separation between this flat band and Dirac band is actually protected by the mirror symmetry of the system. But once you break that mirror symmetry by applying the so-called displacement field, a perpendicular electric field to the device, actually there's no longer that protection. So then these two bands start hybridizing. Okay, so by controlling this displacement field, you can actually tune the bandwidth and the band structure sort of continuously in situ. And how do we do this kind of thing? It's very similar to how we achieve doping, but this time we put two gates, one on the top, and the other one on the bottom, and then you can actually independently control both the charge carrier density, the doping, and the displacement field by tuning the two different gates and some combination of them. Okay, so that's sort of the device, and here's an example of the device, typical transport device that we make for this kind of sample. Okay, so we can just go directly into the data. So this is the resistance map. As a function of the y-axis is the displacement field. The x-axis is the same new filling factor that I was talking about. It's still ranging from 0 to ±4, where the ±4 is telling you the band edge of the flat band, where you have some signatures of some superlattice gaps. But here you don't see actual gaps because you still have the Dirac cones. So there are so many things going on, but I just want you to focus on these blue regions of zero resistance, which is the superconducting region. And you can already see that the regions where superconductivity appears is very tunable within both the displacement field and the filling factor in the system. Okay? And it's not just the filling, it's not just the extent of the superconducting dome, but we can actually measure the TC of the entire phase space, and then this is the map of the TC actually, and you can see that the actual TC is also controllable in this phase space as a function of displacement field and charge carrier density. And it doesn't just stop there. It turns out that it's not just the TC, but we can also control the strength of the superconducting pairing itself as well. So for example, we can go to some high displacement field region and tune the superconductivity into this ultra strongly coupled regime. So what this means is that, for example, here we have the superconducting coherence length as a function of this doping density. And you can see that this coherence length is actually in the order of the same order as the average interparticle distance. So that actually means that your Cooper pair size is at most that interparticle distance, or even smaller than that, which is very different from the typical weakly coupled BCS superconductors, where your Cooper pairs are kind of, the size is very large and they're far away. And another evidence for the same kind of physics is that you can measure this quantity called TC. So TBKT, you can for now just think of it as TC for the superconductivity over the TF, which is the Fermi temperature. And that ratio, in simple terms, basically sort of corresponds to the ratio of the superfluid density over the electron density. So what this quantity sort of tells you is that among all your available, electrons or like workers, like how many of them could contribute to formation of Cooper pairs or superconductivity. And this value of like over 0.1 for 2D superconductors is considered actually theoretically very high. So this is another evidence that we have very strongly coupled superconductivity that could be even very close to BCS-DC crossover regime. So we have the strongly coupled superconductivity, and there's this thing called UEMRA plot, where you're basically gathering all of these different superconductors around the world as a function of this the x-axis is the electron density, so it's similar to the Fermi temperature or the electron density of that ratio. This y-axis is the TC. So that's basically, it tells you sort of this ratio in one map. And you can see that in the lower right corner, where you have large electron density, but then low TC, that's not like, honestly, that's not that efficient of a superconductor, right? Like you have these weakly coupled BCS superconductors like aluminum right here. And as you move towards the upper left corner, you see this band of different materials consisting of a lot of unconventional high TC superconductors with relatively higher ratio of the TC over TF, okay? And when we try to place our magic angle twisted trilayer graphene, it's right here. So we could see that it's one of the most strongly coupled superconductors. So that's cool, but like, why would you care about strongly coupled superconductors like at all, right? Other than the fact that maybe it's kind of exotic. So I think like you can understand it in a way that, you know, even though our TC is like only like 2 Kelvin, 3 Kelvin order, right? So it's not actually that high, especially compared to the actual high TC superconductors. But what this sort of high ratio of this thing tells you is that our TC is actually very high for having such low carrier density in the system. We have almost atomically thin superconductivity. So understanding how this kind of, you know, superconductivity may form might also provide actual design principles for future actual, maybe better high TC superconductors as well. So there's that motivation for that. That's what people might care about that plot. Okay, and in addition to that, I wouldn't go over into detail at all, but I also want to mention that in the same system, we found that the critical magnetic field in the in-plane direction was exceeding the nominal Pauli limit by like 2 or 3 times across the entire dome. So this sort of tells you that the spin structure of the superconductivity might also be not simple BCS spin singlet type of structure. Okay, so we looked at twisted trilayer graphene, but I want to mention that that's not the end of it, because, you know, as long as your structure is this same structure where you have this alternating plus theta minus theta plus minus theta blah 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 up until whatever number of layers you can experimentally realize, honestly, you would still be able to form some sort of magic angle with exactly the same principles, where you can block diagonalize this very big Hamiltonian for the number of layers, and you can always try to make one of the blocks into a flat band like block, so that you have the flat band, and then the other bands will just be kind of existing there. And this is actually a very good system for answering our original questions that we started with, because we always have this exact same band with the same C2T symmetry, but then you have these other bands coexisting. So you can see the band structure for 2, 3, 4, 5 layer, they all share this flat band with some other bands coexisting for the other number of layers. You can also do the displacement field control. So, yeah.
Yeah, so in the band structures, does all layers contribute to the flat band?
Yeah, yeah. So, well, not all, but it's combinations. So it's not like you can only think of like the top 2, or like it's a hybridization. So you can sort of think of it as bonding and anti-bonding orbitals. Okay, so we have experimentally realized this system up to 5 layers. So you can see the resistivity versus temperature for magic angle twisted bilayer graphene, twisted trilayer, twisted 4-layer, and 5-layer. They're all pretty superconducting. So we have found this family of strongly coupled superconductors now. And obvious thing that you also want to study is, you know, compare and contrast what these family members have in common and difference. I'm not going to go into detail. If someone is interested, you can read this paper. Okay, so we can come back to the original questions that we were asking in the beginning of this particular section. Can we design a new Moiré system that opens like a new dimension to study that? Superconductivity and magic angle graphene, yes, like we made this magic angle twisted trilayer graphene, which opened up this extra dimension in the displacement field, a lot of tunability, and found some exotic signatures of potentially unusual superconductivity. Can we find some important ingredients or recipes for forming this magic angle superconductivity? The answer is also yes. Like we formed an entire family of these structures where, you know, you share the same type of flat band and symmetry, but different in other aspects. So the obvious questions at this point then would be like, okay, this is all cool, but what's the actual physics that's going on? What's the underlying electronic structure? Or, you know, what's the order parameter of the superconductivity of this entire family? And eventually, yeah, like everyone still wants to ask, how are you going to increase the TC? So let's first just focus on the first question. What is the underlying electronic structure? So in the beginning, I mentioned that it's important to think of this fourfold spin and valley flavor symmetry in the system, that you have this degenerate 4 flavors that's existing, that's sort of inherited from the graphene structure. Okay, So now the question is, is this symmetry still present in our system? And if that's still present, why would your phase diagram look so different at different filling factors? And why is your superconductivity only appearing in these like particular regions? It kind of like doesn't make sense, right? So then there's gotta be something going on with the underlying electronic structure. So then the question was, how can we then better characterize the underlying electronic structure of this magic angle graphene? Is there any sort of actually symmetry breaking that's important? Or are there any other important phase transitions that's going on? So these are the questions that we want to answer next. So there goes that second part where we sort of made use of van der Waals header structures also as like a new kind of measurement platform to study these thermodynamic properties of the magic angle graphene. Okay, so before going into the details of the experiment, I still just want to give you an overview. So typically, when we try to study some sort of many-body physics in these material systems, there are sort of two different routes in terms of learning about that. One is the excitation type of measurement, where you're trying to probe the available excited states above or below the original Fermi energy. So that sort of includes the techniques that we're sort of familiar with, at least for hearing, like STM, like RPES, scattering, and all these measurements or excitation type of measurements. But there's a complementary approach of where you can actually measure this quantity called chemical potential. And that's actually now, instead of trying to probe the available states, you're actually directly tracking the ground state energy itself as your electrons are adiabatically added or removed from your system, okay? So one very like pictorial analogy that I like to make is that you can imagine this sort of water bottle, which can sort of change its shape as you pour or remove water from this water bottle, okay? So that water bottle shape is sort of the many-body density of states. And the excitation type of measurement would be measuring like for a particular water level, you want to measure the entire shape of the entire bottle. And then you can also, of course, do it as a function of gating, but one measurement itself would be measuring the shape of the bottle. Whereas in the chemical potential or thermodynamic kind of measurement would be you're measuring this water level itself as you add the water, okay? So you're sort of tracking how this water level changes as you are adding or removing more water. And of course, if you don't have any many-body interactions, it would be like the two things will be basically measuring the same thing in some sense because your water bottle is just like rigid and not really changing in shape. So that's the context. And today I want to sort of first talk about how we can measure this chemical potential, this water level itself. So but another motivation for learning this chemical potential is actually that once you have the chemical potential as a function of other variables, you can also get other thermodynamic quantities. For example, if you know it as a function of temperature, you can know entropy. If you know it as a function of magnetic field, you can also obtain the magnetization from these measurements through this, our good old Maxwell's relations. Okay, so then how are we actually going to measure this kind of quantity? So of course, there are so many other techniques that are very fancy, but imagine you don't have those machines. How can we achieve that? So we thought of a technique where we can actually just directly sense the chemical potential of this magic angle twisted graphene layer using another monolayer graphene that's very close by. They're only separated by this very thin dielectric, okay? And they're all separately sort of contacted and whole bar and gated. And in this regime, basically what you can do is that if you measure the transport of both of the layers, the chemical potential of one layer, let's take for example, chemical potential change in the magic angle twisted graphene will be reflected in sort of the phase space map of the monolayer graphene. So if you can track how your Dirac point moves in the phase space, you can actually directly convert that into the chemical potential of the magic angle twisted graphene, and that's because that's just using the screening properties of the materials. If you have a metal, like it will be screening a lot. If you have an insulator, it will be screening less. The effect of the backgate. So if anyone's interested in the actual details, I can talk to you later. So through this, we can directly measure chemical potential simultaneously with the regular transport measurements. So here's the map of this chemical potential as a function of, again, our already familiar, this filling factor nu from 0 to plus minus 4. So now this plot was kind of weird, okay? And that's because it's not linear. So normally what we imagine when we change our doping density in the system is that you're like changing the chemical potential as well, like you're literally filling up linearly. So then in a very simple system, you would expect this to be a linear thing, but obviously it's not linear. Rather, you have these bumps where the minimum is happening at each of the integer filling factors, okay? So that's surprising. So how are we going to understand that? So at this point, we can come back to our original question of what we were asking, what's going on with the fourfold spin and valley flavor degeneracy in the system. So turns out that we can understand this shape as a spontaneous breaking of the flavor symmetry due to strong interactions in the system. So let's imagine this is the charge neutral point, and you're like filling your electrons starting from 0. And originally, you would be filling all 4 flavors together because like it's supposed to be degenerate. So you would just start filling kind of all together. But what this means is that you have all these 4 flavors on each of the sites. So as you keep filling, at some point, there's going to be a phase transition because you have so much on-site Coulomb interactions. Okay, and then you would actually want to polarize into a single, flavor because you would rather prefer to have just like 1 electron per site. So that would doing this polarization would actually first minimize your Coulomb repulsion on site. So that's the first effect. But in that case, like you would just sort of like expect like a plateau. But what we actually observe is actually this thing going down, okay? So you have negative compressibility. And this part, we can actually explain it in terms of it's not only minimizing the on-site Coulomb repulsion, but it's actually also sort of giving you the benefit of the maximization of exchange energy. So you can think of the Hund's rule, atomic physics or like general chemistry. If you you polarize into the same state, you actually have a lot of exchange energy gain. So you also have this energy gain. So it actually can actually go into even lower energy. So that's eventually you reach this minimum point by fully polarizing into a single flavor. And after that, you would just like keep filling. But beyond nu equal to 1, I think the picture is slightly more complicated than just like, oh, this thing now goes down and might be more rearrangement going on. But basically, this is sort of a picture that's going on. So the point that I want to make here is that there is this spontaneous breaking of the fourfold flavor symmetry due to the Coulomb interactions. And why do we care about the fact that there is such symmetry breaking? Because that means that the electronic structures in different points of the phase space near different filling factors, they're like not the same because some sort of symmetry is broken, so they're different structures. So that's sort of the point that I want to make, what we can learn from this measurement. And the same exact kind of physics was probed using other techniques, including scanning SCT that's sensitive actually now to the derivative of the chemical potential called the compressibility, and also the STM measurements done here at Princeton. They're all showing the fourfold flavor symmetry breaking that's going on in the magic angle graphene system. So this is sort of a standard understanding now. So we don't want to sort of stop here, but because with the measurements, what we just learned is that, okay, in this one line, which is magic angle bilayer graphene, we had that symmetry breaking. But remember that we also have this one more dimension. We want to still make use of that dimension because many things are going on, and then we can still correlate the underlying electronic structure with other phases that's showing up in transport. So what we can measure is this thing called hole density. So hole density, you can basically think of it as like reflecting the type of carrier that you have. Is it an electron-like carrier or a hole-like carrier? And if you measure this hole density as a function of this, doping level or filling factor, you can actually observe sort of the changes in your Fermi surface shape. Okay. So for example, there's 3 examples. The first one is like gap or Dirac-like behavior, where your hole density is actually, as you increase the doping level, your hole density just linearly crosses zero and changes the polarity, like changes the sign. So like hole-like carrier turned into electron-like carrier. That's like a very simple gap or Dirac cone-like behavior. And this is happening at like charge neutrality point, which like where it's supposed to happen. And another type of hole density feature is this resetting type of feature, where you're originally filling this hole density like kind of linearly, but then all of a sudden it like jumps. And then at some point it just suddenly drops to zero. It resets to zero hole density and then starts refilling. So this kind of resetting feature is also happening at these, the color to white transition points at like integer filling factors at low displacement fields. And the last type is this Van Hoff singularity, where basically your hole density all of a sudden goes to infinity, and then again all of a sudden changes the sign. So this sort of Van Hoff singularity shows you that there's some sort of saddle point in your Fermi surface. So this kind of Van Hoff singularity features are happening at these very high displacement fields in certain regions. Okay, so these are sort of hole density, which can tell us more about the electronic structure. And now we can sort of compare side by side this two plots, the transfer resistance plot that we saw with the superconductivity and this hole density. And like already you can see that there's a striking similarity just by like literally looking with your eyes. Like there's something very similar. We can't pinpoint exactly what, but there's some similar features. So we want to understand this more systematically, so we can put it into a single plot where the superconductivity is now with this light blue color regions, and the hole density features are color-coded with these different colors. And the first thing that you can actually realize is that these superconducting regions, okay, are exactly actually bounded by both the reset and Van Hoff singularity features, where something is going on for your Fermi surface. Okay, so that sort of already tells you that, okay, superconductivity must be related to some sort of this symmetry breaking that's going on in the system in these particular regions. So just to sort of show you once more, like what would happen at this kind of boundary at the Van Hoff singularity, the effective mass diverges, so it confirms that you have some sort of Van Hoff singularity at this point. But at exactly the same point, because we can do the transport measurements, at exactly the same point, your TC drops to zero and the resistance becomes non-zero, or vice versa. There's a transition point of the superconductivity, exactly where this Van Hoff singularity is happening. So that again tells you that superconductivity is bounded by these resetting features. Okay, so then now we have some sort of clue that superconductivity is only happening in these particular phases that are particular symmetry broken phases, okay, that are bounded by these transitions. So then what are these symmetry broken states? So we can actually try to obtain what kind of symmetry broken carriers are dominant in all of these regions by measuring the quantum oscillations, which basically sort of tells you the broken degeneracy of the system. And you can measure basically these Landau bands across the entire map, like in all these different lines in the B. And then you can sort of assign what kind of carrier or degeneracy is the most dominant in all of these regions in this entire phase space. And surprisingly, you can see that the result tells us that the superconductivity appears only when your charge carrier is the symmetry broken nu equal to plus minus 2 type, the so-called half-filling carriers. So you once your carrier type changes to either plus minus 1 or 3 or something else, you don't have superconductivity. And normally, if you have just one line, which is the case of magical twisted bilayer graphene, and you still obtain this kind of result, who knows, it might just be a coincidence, right? But now we have the entire y-axis dimension, and it always follows the exact same trend, even though the superconducting dome shape changes and everything, still the carrier density is exactly what's mapped in this thing. So it really tells you that there is a very strong relationship between superconductivity and the so-called symmetry broken half-filling carriers. So then the question is then okay, that's important. What is the electronic structure of these half-filling carriers? And this question was also answered by this measurement actually done at Princeton in Ali's group, where they measured these atomic scale imaging of this, near the half-filling state equal to plus minus 2 states, and found that there is this particular IKS state that has this sort of symmetry in the system. So it seems like that's also relevant for the formation of the superconductivity. And not going to go into detail, but just to also tell you that with this kind of measurement technique, we can also answer other kind of questions. As I promised, you can obtain the entropy, magnetization, and even like charge diffusivity, where you can learn different kinds of things, such as we saw that there was a phase transition, very peculiar, where you have low entropy Fermi liquids reversing melting into high entropy solid states, also called the Moiré effect in the system, and then magnetization status and everything. So if you are interested, you can look into further detail here. So we can come back to sort of now the questions for this particular section. Can we better characterize the underlying electronic structure? The answer is yes, we could directly measure the chemical potential and obtain thermodynamic measurements. We saw that there's a spontaneous breaking of the flavor symmetry, and among those different symmetry broken carriers, the plus minus 2 half-filling carriers are the most relevant for superconductivity, and we could also measure all these other phase transitions and so on. So now, like, this technique has also been applied to other kinds of systems as well, but there's still, of course, remaining questions. Okay, so finally, we can't ignore this question. We've been talking about superconductivity, but what is really the nature of the superconductivity? So there have been different types of experimental evidence pointing towards, the unconventional nature of this superconductivity, including this, we already saw that there was the critical magnetic field violating the nominal Pauli limit in magnetostate trilayer graphene. But on top of that, the STM spectra showed that there's this V-shaped tunneling spectra instead of like a flat bottom U-shaped in these materials. And we also saw this spontaneous breaking of the rotational symmetry in the system in the critical magnetic field direction, which is called nematicity. And more recently, we also saw that there's this linear anti-superpositiveness, but not going to go into detail, but basically all of these and many more other experiments in the past have been pointing towards potentially unusual nature of the superconducting gap. Okay, and there have been many different theoretical predictions for trying to understand what the pairing symmetry in these materials are, and also many different theories trying to understand the mechanisms that lead to that whatever kind of superconducting gap there is. But even to this date, we don't really have the answer of what the pairing symmetry is. Okay, and why? Like, why is that? It's been already like 7 years since the discovery of the superconductivity in the magic angle graphene. And that's actually because, when you try to study the superconducting gap, you need to be using some experimental technique that's like sensitive to the superconducting gap structure, okay? For example, you want to be measuring something like the density of states of the system, where you might be able to capture this, full gap versus nodal gap with the flat bottom density of states versus linear density of states. Or you might want to do some phase sensitive measurements like Cornell junctions or Josephson junctions that are done for the cuprates to sort of definitively tell the D-wave symmetry in the cuprates. So those are the kinds of measurements that we want to do. However, there's a little bit of problem in Moiré, superconductivity. First of all, the energy scale that we're dealing with is very small. It's like, all these correlated phases are mostly like milli-electron volt, and the superconducting gap or something like that might be even smaller than 1 milli-electron volt. And even within such small energy scale, there's so many different phases that's coexisting in this phase diagram. You have superconductivity, correlated insulators, potential pseudo gap, translator, blah, 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 so many things going on, symmetry breaking, okay? And on top of that, it doesn't help that, each device might have a little bit of doping variation because of the unfortunate twist angle disorder, or just like the details of the device, you end up in different twist angles in general. So it's kind of hard to compare, just among different sets of experiments, or even similar sets of experiments but done on different devices. Like, it's hard to have apple-to-apple comparison. For example, like, the fact that there must be superconducting correlating insulator, that's kind of universal in all the devices, but the exact extent of the superconducting dome, how much it overlaps with the correlated insulator, up until where in doping is the superconducting gap, up until where in temperature is the pseudo gap or versus whatever, like all these details are quite varying in different, devices and different setups. So, then now the question is then, in this kind of scenario, how can we then identify or isolate a superconducting gap? And if we can do such thing, like what would be the nature of this gap? So as you saw in the previous slide, we would greatly benefit from a multifaceted measurement approach where we can simultaneously do some measurements that's sensitive to the superconducting gap, but also be able to check other aspects of superconductivity that was already seen in the previous measurements. And so there goes the second part of this, this interval space multimodal measurements technique. So now this is our device structure. Now we have 12-layer stack where you couple basically magic angle twisted trilayer graphene with another magic angle twisted trilayer graphene with a 3-layer thin tunnel barrier of HBN. Okay, so that's like a typical structure of tunneling junction that you can think of. But here, the important experimental thing that we did is that we actually made sure that there's another, kind of thin but not tunneling tunneling thickness, HBN, that's also coexisting here, and we open up this circular window here, okay, in the middle of our device. So that the tunneling between these two devices, regimes only happen in this very center region. And where's the center region? The center region is exactly where you would be measuring the core of the whole bar devices of both magic angle twisted bilayer graphene and another twisted trilayer graphene. Okay, so with this kind of design, we can independently dope both top and bottom magic angle twisted trilayer graphene, and we can etch the entire device into the whole bar shape and do full-blown whole bar measurements. And exactly for the same region, we can do the interlayer tunneling spectroscopy across these two magic angle twisted trilayer graphene between different phases that they have. Okay, so the very first thing you want to do when you make this kind of very complicated structure is to sort of check that you actually made the structure that you thought you made. So here are the resistance maps for the top magic angle twisted trilayer graphene and bottom magic angle twisted trilayer graphene as a function of bottom gate and top gate voltage. And you can actually see you have all the features that are common in the magic angle graphene, trigentuality, potential superlattice features, and most importantly, these very dark regions of zero resistance, which is the superconductivity, and that's happening in both of the layers. So with this, we can confirm that we made the structure that we thought we made. So now we can get into the actual business of tunneling. So in order to do tunneling spectroscopy, what we do is to park, our gate voltage for the bottom layer to be in some normal state. Okay, and using that bottom magic angle twisted trilayer graphene in a normal state, we're going to probe and study the top magic angle twisted trilayer graphene. So here is the tunneling conductance map as a function of the top gate voltage, which controls the doping of the top magic angle twisted trilayer graphene. And the x-axis is the interlayer tunneling voltage, which is basically the energy scale that you can probe. So it's a very large scale map. And sort of the first thing that you can realize is the normal state resistance is actually around the value that you would be expecting for a 3-layer HBN tunnel barrier for the region of that little hole that we drilled. So this actually confirms that our tunneling activity is happening in the middle of that core device region where we're also measuring the transport and not some random other regions. So that's a sanity check that we can do. And you can sort of also compare with STM on MATTG, and the large scale features are, you can see that it's very similar. So you can go and take a look at what this map tells you. So what's most evident are these high density of states features where it goes away. And these are exactly the same features that we saw for the fourfold symmetry breaking. So that's called the cascade of transitions, and that's already seen in previous many measurements, including STM. So that's not new. You have this symmetry breaking. That's just that should be happening. But in addition to that, if you go into slightly smaller energy scale, you have these sort of very low tunneling conductance regions, which might be gapped regions. So we want to also zoom in into what's going on there. So you can zoom into very, very small energy scale, which is plus minus 0.3 milli-electron volt scale in the same axis. And you can see that, oh, there are actually these dips in tunneling conductance. So there might be also a gap. So then what kind of gaps are there? So finally, we can make use of the fact that we can do simultaneous transport in the same exact device. We can plot the transport resistance in this scale across exactly the same doping, and then you can see that these two regions are corresponding exactly to the zero resistance regions in transport, which correspond to the superconducting state. And you can also take the line cuts in these tunneling spectra and see that the development of these dips are happening exactly at these superconducting regions. So we have achieved the simultaneous transport tunneling measurements of magic angle graphene, where we could directly correlate the spectroscopic gaps with the dissipationless transport phenomena. Okay, so when we come back to, now we can come back to sort of two original concerns that we had. We had two concerns. First concern was that there might be some doping variation, so then the spectroscopic gap, what phase is it corresponding to? Now, with the simultaneous measurement, at least this concern is gone. Like, we could directly see that wherever we see those, whatever gaps they are, those gaps were corresponding to the superconducting regions. So that concern is gone. But there's still another concern that's remaining for me, where, what if, within the same, within one tunneling spectrum, there might still be different coexisting complex competing gapped phases in a single spectrum in that superconducting phase. So that is still remaining. So we want to still investigate that part. And turns out that that was actually sort of the case. So here's the tunneling conductance now in some intermediate energy range. So wherever we were looking at, we're very small energy scale, like 0.3 milli-electron volt, right? Here in this pink regions. But in addition to that, around a few milli-electron volts, there's also this sort of dip, some sort of depletion of the density of states around those dips as well. So we can take a line cut here, and we can actually see that there are two sets of features. One is this, this smaller, this shoulders that's happening around the 0.1 or something, the electron volt that we saw in the previous correspondence. But in addition to that, you always also have these, broader shoulders that are clearly two separate features from the low energy gap. Okay, so we see that in a single tunneling spectrum, we have two scales. One is the low energy gap scale happening around 0.1 millieV, and then separately there is this high energy gap scale that's like 1 or 2 milli-electron volt. Okay, and now we now we want to sort of investigate then what's going on here. And we can do that first by trying to increase the temperature and see what happens. So here's that same curve ranging from 110 millikelvin up to 1.6 Kelvin. You can see that these lower, first of all, the zero bias conductance gets immediately lifted. And these little conductance coherence peaks in the low energy scale are gone around 1 Kelvin. But these broader shoulders, these high energy gap features are still remaining, okay? And now we can also take advantage of the simultaneous transport measurements also as a function of temperature. And we can obtain that, okay, TC is around 1 Kelvin. And that's actually exactly where these low energy gap features are gone. So, that's one observation. Then now we want to sort of know then what are these other shoulders. So we can keep increasing the temperature and see that, actually up to 7 or 8 Kelvin, it's persistent, but then it's finally gone at such high temperatures, okay? And another thing that we can do is to sort of track the zero bias density of state in terms of the temperature, and you can plot here. And you can see that there's a clear transition around exactly TC where the low energy gap feature transitions into the high energy gap feature. So from this, you can already sort of see that, okay, it looks like the low energy gap is something that's superconducting gap, and this high energy gap with these shoulders might be just something else, okay? But we can't be like 100% sure because it's temperature. Who knows what's going on with temperature? So we want to do another check now with the out of plane magnetic field. So we can do basically similar measurements with the out of plane magnetic field from 0 Tesla out to like 0.6 Tesla. Again, very similar behavior, and you can compare with the transport measurements. The zero bias conductance immediately gets lifted. These coherence peaks are gone around BC. And however, even if you apply the out of plane magnetic field up to 1 Tesla, those high energy gap features, the shoulders, are just like very persistently remaining. And I can tell you that in transport devices, there is no device ever reported that has surviving superconductivity even beyond 0.5 Tesla. So from this, it's sort of, again, evident that, okay, the low energy gap is the superconducting gap, this other thing, something else, whatever that is, okay? So now, at least we sort of got rid of this mystery. Is there coexisting stuff? There seems to be coexisting stuff. So then, okay, what are we going to do? We want to study the superconducting gap, but we also just learned that this curve contains like 2 different things altogether. So then how are we going to only isolate the superconducting gap apart from this coexisting high energy gap? So we can, again, take advantage of the fact that we have this the superconducting curve and learn from the Cupric community to normalize the curves with the curve that's sort of right above the TC, so that you sort of normalize out whatever the higher gap contributions and only get to be left with the superconducting contribution to the tunneling curve. Okay. So when we do that, the curve looks like this, and we want to now study this curve with this, the tunneling density of states is tunneling conductance is proportional to the density of states, and there's some standard Dyne's formula that you can use for both S wave, gapped phase, and also some sort of nodal pairing for both P and D waves. But in addition to these fits, we incorporated another factor, which is the distribution of the superconducting gap, because we know for a fact that we're not doing like atomic scale tunneling, like we have this finite size tunnel junction, which it's likely that there might be some, superconducting gap, like twist angle disorder, maybe the TC and gap size are different. So we also take into account this sigma for that. And we try to fit that using the nodal fit, fits pretty well. You can also try to fit it with S-wave fit, it's not that good. But I just want to make sure that, okay, like some of you might be, oh, did you just like pick the good looking fits for the nodal fit? I want to assure you that we sort of explore the entire phase space that's possible with all these different parameters, and this is the best fit that we can obtain for the S wave. And so the nodal fit fits better, but some people might be like, okay, this is still just fitting, like we can fit whatever, so maybe not the conclusive statement. So we can do further measurements of now increasing the temperature and looking at how the superconducting curve changes. So these are the normalized curves. You can fit the superconducting fit with the nodal gap that we used in the previous slide, and then now plot this magnitude of the gap size as a function of temperature, and you can see that up until TC, there's not so much change in the gap magnitude, but around TC, it suddenly sort of drops. But in contrast, when you track the zero bias density of states, it actually immediately fills in and linearly fills in exactly up to like TC. Okay, so this is a very typical nodal superconducting gap behaviors. But still, okay, some of you might be, oh, this is temperature, like you might just be exciting some other things, blah, blah, blah. So then we can do further measurements. Now we can do some complementary measurements of using magnetic fields to perturb the density of states of the superconductivity. Okay, so we can first look at what happens if you apply out-of-plane magnetic field. So typically in nodal superconductors, there's this thing called Bolovic effect. If you apply out-of-plane magnetic field, basically you have some Doppler shift in the superfluid velocity around the vortices that contributes to finite zero energy density of states. So what this tells us is that in our case, if you have nodal superconductivity, Bolovic effect will result in this zero bias conductance having square root of E perpendicular behavior. So that's sort of the expectation. And we can see what happens. So this is the transport superconducting dome as a function of out-of-plane magnetic field. You can take some line cut at some optimal doping and look at what happens in the tunneling curves. And we can track that 0 density of states and plot it as a function of B perpendicular. And you can see that exactly up to or around up to like BC that's measured in transport, actually this trend fits the square root of the behavior, which again aligns with the nodal superconducting gap. Another thing that we can do is to apply in-plane magnetic field. And again, what happens for the nodal gaps, due to time, I'll just quickly go over, but basically for nodal spin singlet superconductor, what you would expect is that you have a linear dependence in the Zeeman field for the 0 bias density of states. And we can check what happens in our case with similar measurements. So here's that tracking of the 0 bias density of states. You can see that it immediately fills up, but it's not necessarily like, it could be interpreted as either like you have linear, but with some thermal broadening at this 300 millikelvin scale, or you might not have this linear dependence, but this dependence might actually be coming from potential orbital coupling in the structure. So this itself sort of still tells you that it's likely to be nodal, but whether it's spin singlet nodal or it might be some other complicated spin structure nodal and plus orbital coupling that needs further investigation. Okay, so we saw sort of 4 independent evidence for nodal surrounding gap, and all aspects were confirmed with the simultaneous transport measurements as functional of these different variables, and this is also reproducible in both the electron and hole side of superconductivity. And remember, we also had the other layer of the superconductivity, so that's also confirmed in the other layer of the same device, and this is also reproducible in another separate, totally different device. Okay. And just one last thing that I want to mention is that we can also look at the doping dependence of the superconducting gap. So here's sort of the tunneling spectra as a function of the top gate voltage. This is across the superconducting dome. And next to it, I want to just put this totally different measurement, which is the resistance as a function of temperature and doping. So these are kind of unrelated measurements. One is tunneling spectroscopy. The other one is just like temperature dependence of transport. It's just in the same device. And now I want to extract the nodal gap from this tunneling curves and then put it on top of the superconducting dome. And then you can see that it actually follows very well. And it happens again in the electron doped side. You can even actually catch this little kink in this superconducting TC. So it leads to an interesting conclusion that the superconducting gap actually follows the shape of the TBKT across the dome. And from other kinds of measurements using superfluid stiffness, we saw that superfluid also follows the TBKT. So this means that the superconducting gap also follows the superconducting stiffness, which is kind of, it needs further theoretical understanding of what's exactly going on here. But this at least once again shows you that this is the superconducting gap. Okay, so yeah, and then in Philip Kim's group, we also saw another evidence for the nodal nature of the superconductivity, which is the superfluid stiffness showed the linear NT dependence. So just another evidence appearing at the same time. Okay, so we can sort of come back to the questions. Can you identify superconducting gap? Yes, we could just use fully Van-der-Waals device-based measurements to do simultaneous measurements. We could directly correlate the gaps with the transport features where we were able to sort of distinguish the superconducting gap from other gap and isolate that superconducting gap, and that superconducting gap seems to be pretty nodal. So now an obvious next direction is that, like, okay, if you think that superconducting gap is like nodal, then like can you try to find the direction of the nodes? We can actually sort of do that sort of experiment using the angular magnetic field dependence of the superconducting gap, the in-plane Limiticity measurements, but using tunneling spectroscopy, and we actually obtained recent results that it shows very strong two-fold limiticity in the tunneling gap as well. And this technique is just broadly applicable to the other kinds of emerging 2D superconductors as well. So today I just sort of talked about how this sort of like, well, not history, but like the flow of what kind of research we could do to investigate this, imagining multiphysitic graphene family, and the kind of questions and what kind of techniques that we could use to investigate and answer those questions, and how that feeds into this, cycle. And simultaneously, since I'm running out of time, very briefly mention, as other people also mentioned, there's so many different materials happening, including twisted TMD or molecular graphene. But the point that I want to make is that now the Moiré quantum matter is really showing phases that were just never observed through any other means, like the fractional quantum Hall effect. This is the first time. So, so then it makes sense for us to, okay, we want to keep expanding this phase diagram of Moiré quantum matter. Okay, but for what? Well, what are we going to expand this for? So here's sort of, some summary of, the phases that were found so far, but, it's, since there's something new getting updated in archive every 3 weeks, so maybe I'm missing some of the recent ones. But basically, we have so many phases. So one direction could be trying to find the phases that were not found yet, like non-abelian, even the non fractions at zero field, or some other novel phases matter, like topological superconductivity. But another sort of important direction is that if you look at all these phases, most of them are happening at liquid helium temperatures, and in device with sizes that are like at most a few microns squared. And then I already mentioned that there's difference between different devices, and that's not limited just to twisted graphene structures. It's also this case for non-twisted structures, different devices showing different results. So obviously we need better reproducibility with higher transition temperatures for all these phases, and some scalability for larger devices. So for that, I think we need some experimental improvements that can actually do some systematic investigation of what's actually the important thing, and sort of discern between the details and the fundamentally important aspects. So 2 examples that I think was already mentioned in the previous talks, but one is the in situ twisting with QTM, where Ilani group first discovered, but many other groups are also doing. Also Yuan was doing it with MEMS yesterday, basically the same thing. And then another direction is also Jeannie mentioned today, but there's a group where at Chicago where they're sort of developing this robot to do very large scale van der Waals assembly for these twisted materials as well. And I just want to also mention one last time that there's a new sort of fabrication method paper that our student recently wrote that sort of summarizes the fabrication technique that is in Pablo's group. Okay, so yeah, with that, who knows, like we might actually be getting close to realizing some topological quantum computing in 2D materials. And yeah, thank you for listening.
Any questions?
Thank you. Thanks for the nice talk. Maybe very naive question. So I can see the increasing number of stacking layer graphene. So what is the kind of number limit for stacking the number of graphene? You can still have the flat band, so you can see a strongly correlated property. Yeah, right now I see the number maybe 5 to 6. Yeah.
So
can
for
you do like 10, 12?
I guess in principle you can do 10 or 12. Just one kind of issue when you have so many layers is that when you try to gate them, there might be some screening effects from the outermost layers. So I think I briefly mentioned that this flat band is not just like a few layers, but it's sort of a superposition of like all these different layers. So in principle, if you want to gate fully the flat band, you want to be able to reach the middle layers as well. But then if you have so many layers that are stacked on top of each other and you try to gate with the gates on the very top and bottom layers, the electric field might not be reaching the same amount in the core of the region. So there might be a little bit of issue with the doping in general, if you have just so many number of layers of graphene, not necessarily just twisted, but yeah, at that point it's like graphite. So, yeah.
Yeah, very nice talk. I was curious, do you have any idea about what that higher energy gap might be, if it's an interesting phase, or if it might actually tell you something about the sort of character of superconductivity that arises from it?
Yeah, so that's a good question. So it seems like, oh, hold on. I can show you that. Oh, actually. Oh, I might have deleted, sorry, I might have deleted the slide, but we also investigated the high energy gap feature as a function of doping. And then that actually also roughly follows the superconducting dome shape. Not exactly as much as the superconducting gap, but it's like, it's not having the behavior of the so-called cuprate pseudogap, where like it's not following the superconducting dome, but this is still sort of happening kind of only in the superconducting region and sort of roughly following that shape. So our current understanding is it's gotta be related to the formation of the superconductivity, but honestly, like we don't know what it is, and we, like it's some sort of pseudo gap, but that terminology might be controversial, like because some people might think that pseudo gap should only be referring to cuprate pseudo gap, but yeah, the current evidence is that it's definitely related to formation of superconductivity, but unclear exactly where that's coming from. So we are actually also planning to do some measurements of the nanoticity in the higher energy gap, so that it might also reflect some of their nature.
If there are no further questions, let's thank the speaker again.